Hi everyone, this is part 2 on solving log and exponential equations. And just as a reminder, what we did in part 1 is we learned the basics and we focused on some more simple equations when there was only one log or exponential function in each equation. And now we're going to look at some more complex equations. So the first thing I want to do is take a look at an equation that has two. So it has two either log functions or exponential. It won't be one of each. That would be a very difficult question. But an equation that has either two log functions in it or two exponential functions in it and nothing else. So what we would do in this problem is, first of all, separate them. If they're the only two things in the equation, it's almost automatically going to be separated already. It's going to be one thing equals the other. But just in case it said like, one log minus another log equals 0, just add that second one to get them on opposite sides of the equation. Then, when you use your inverse properties to cancel either one of them, what's going to happen is they both cancel out. And then you just go ahead and solve. It ends up being a pretty straightforward, simple question. But do remember, just like we talked about in part 1, if you have a log equation, you still need to check for extraneous solutions. So let's try one out. We have the log base 4 of x squared minus 2 equals the log base 4 of negative 2x plus 1. So this is exactly what I described to you guys. We have two separate log equations. They both have the same base. That's good. And there's no third term. There isn't like a plus 10 on the end, or a plus, or maybe another log, plus log base 4 of x on the end. If you have that third term, that's what we're going to talk about in just a few minutes. But for right now, just the two functions, and that's it. And I said it ends up being a very simple problem, because when you go, first of all, the first step is to separate them. But like I said, most equations, they're already separated. One log equals the other. So then we want to cancel them out. We go, well, if I want to cancel out a log base 4, I'm going to use a 4 to the x. I'm going to use an exponential base 4. So this is one of those questions where what I like to do is just leave the equation written, basically turn the equation into the exponent, take a base of 4 and raise it to each side power. Now, in part 1, when we did that, it usually went like something like this. Okay, so this cancels and then you finish solving. Well, this is actually even easier because they both cancel. You're using a 4 to the x to cancel out both of the logs, and you end up with just what was inside. So you end up with just x squared minus 2 equals negative 2x plus 1. And now it's just a quadratic. I mean, it's an easier equation to solve. Now, because it is a quadratic, you have an x squared term and an x term. We want to get everything on one side, have it equal to 0. So I would start by adding 2x to both sides. I'll kind of squeeze that in the middle there. I would also subtract 1 from both sides. I'll just do both steps in one line like this. And basically what you get is x squared plus 2x minus 3 equals 0. And when you get a quadratic, remember you have two choices. You can try to factor it. And if it's not factorable, you can do quadratic formula. This one is factorable. It factors into x plus 3 times x minus 1, which gives me, and I'll call them possible solutions for right now, gives me possible solutions of negative 3 and positive 1. And the reason I said possible solutions, remember this was a log equation, which means those could be extraneous solutions. We need to test each one. So let's go back up to the very original problem. And let's start with the 1. I like the 1, it's easier. So if I plug in 1 for x, I have log base 4 of 1 squared minus 2 equals log base 4 of negative 2 times 1 plus 1. I kind of ran out of space, but we'll squeeze it in there. Now what happens on the very first one, you get 1 minus 2 is negative 1. I don't even need to see what that second one equals. That's what causes extraneous solutions. You can't take the log of a negative. So even though it looked like 1 was a solution, it's actually what we call an extraneous solution because it can't be a solution. If I plug 1 in for x, I get undefined. And if something's undefined, then it didn't work. So we're going to throw out the 1. That's definitely not an answer. And then let's try the negative 3. So if I plug in the negative 3, I would have log base 4 of -3 squared minus 2 equals log base 4 of -2 times -3 plus 1. And that would be log base 4 of, that would be positive 9 minus 2 is 7. And on the other side, it would be positive 6 plus 1 is also 7. That one works. Log base 4 of 7 equals log base 4 of 7. So the -3 definitely does work, but the 1 didn't. And that's our first example that we worked out together that was an example of an extraneous solution. So the only answer to this problem is -3. Even though our work told us the answers were -3 and 1, we ended up throwing the 1 out because it was extraneous. Okay, for our next example, I'm going to do the same situation but exponentials instead of logs. So what we have in the last example, we had 2 log functions that were equal to each other and no third term. This time we have 2 exponential functions that are equal to each other, but no third term. And we also have a problem here because we don't have the same base. And I did say in the notes, you want it to be in the same base. If I want to cancel out an exponential, I want to do it by using logs. Well, if I have different bases, I can't do that. So when I look at this problem, the first thing I notice is I have a 3 to the x on one side, 3 to some power, and a base of 9 on the other side. So I can't cancel them out right now, but 3 and 9 are related by exponents. 9 is 3 squared. So let's just make that substitution. Let's leave the problem right now, leave the left-hand side as 3 to the 5x plus 1. Let's just rewrite that 9 as 3 squared. Now, we have a rule of exponents. When you raise a power to a power, you multiply those exponents. So what I really have here is 3 to the, I'm going to multiply 2 times 2x minus 7. And if I distribute that 2, I would have 4x minus 14. So now what I've done is I've essentially changed the base. So now I have an equation where they are both base 3, which is what I wanted, and that means I can cancel them out by taking the log base 3 of both sides. So I do that. I take the log base 3 of both sides. That cancels, that cancels. We just end up with the exponents equal to each other. 5x plus 1 equals 4x minus 14. That's an even easier equation to solve than the last one because it's not quadratic. We don't have to factor. We just have to solve for x. So let's subtract 4x from both sides. We get x plus 1 equals negative 14. Subtract 1 from each side. And our final answer is x equals negative 15. And I did say final answer because this was an exponential equation and those don't have extraneous. You can check your answer if you want. Like if you go back to the original problem and you plug in negative 15 for x, you'd probably want to use a calculator to do it, but you should get the exact same answer for both. All right, so that was an example of one log and one exponential equation when you have 2 functions in the same problem, but nothing else, just those 2 functions. So for our next step, let's talk about when there is a third term in there. So I said you could have 2 or more logs. We'll do same base again. And there's going to be some sort of third term. It might be another log added onto the end. It might be just a number plus 5 or something. There's 3 terms, 3 or more terms instead of just 2. What you want to do in this situation is go back to our properties of logs and actually do a condensing problem. And I mentioned this in 7.3. I said this is one of our main uses for condensing. If you have more than one log in an equation that you're trying to solve, you can condense it all into one, and it makes the problem more simple. When you do the condensing, what happens is depending on the setup, it will automatically turn into one of the 2 types of problems we've done. It'll either turn into something from part 1 or the one I just went over with you a few minutes ago. So let's try that out. And then you solve for x, of course, at the end. All right, so what we have is a natural log question here. There are 2 separate natural logs. We have natural log of x minus 3 plus natural log of x plus 3, but then it equals 4. So you got that extra term there. If it equaled 0, then we could separate and it would be more like the question we just did before, but not this one. So this one right here, we got that third term. And when you have the third term, we don't want 3 terms. So I'm going to start with a condensing problem. I'm going to go back to section 7.3, and I'm going to combine these two into 1. So we can do that. I mean, we just finished doing that. We'll combine it into one single natural log. Now the rule is when you're combining logs that are being added together, you take the two things in the logs, the x minus 3 and the x plus 3, and you multiply them. That was our u times v property. So that's the condensing part. All that work in green right there, I took those two natural logs and combined them into 1. Now it still is equal to 4. I haven't done anything to the 4 yet. But what you notice is, see, now it's basically a day 1 equation, a part 1 equation. Instead of having 2 separate natural logs, we only have 1. And the rule for having one log function is step 1, isolate it. Well, it's already isolated, it's by itself. Step 2, switch forms or cancel. Now to cancel out a natural log of x, you use an e to the x. So my next step for this problem would basically be this. Turn the equation into the exponent, turn it into an e to the x problem. Now the e to the x and the natural log of x cancel. So you get just what was inside, which is the x minus 3 times x plus 3. And now it equals e to the 4th power. We want to solve for x. The next thing I would do is multiply it all out. And you could have done that right off the bat too. Yeah, you could have multiplied the x minus 3 times the x plus 3. It's actually a difference of 2 squares, and it ends up just being x squared minus 9. And then we'll add, and now we're solving for x. It's the solving part, so I would add 9 to both sides. We get x squared equals e to the 4th plus 9. We take a square root. And what I have right now, I'm going to write them out separately. First of all, we get a plus or minus. I want you to all remember that. Anytime you take the square root when you're solving an equation, you always get 2 possible answers, a plus or minus. And I'm actually going to write them out separately because we need to test them anyways for extraneous solutions. So x could be positive square root of e to the 4th plus 9, or negative square root of e to the 4th plus 9. That's my plus or minus right there, basically. Now, when you go to test, this is obviously a very messy one. You're not going to test this by hand. You would probably want a calculator and type it all out. What happens, well, one thing I can do without a calculator is just by looking at the problem, I can tell that the negative one is extraneous. And the reason is, if you look just at this first natural log function right here, if I take a negative number, which is what I have, negative square root of e to the 4th plus 9, whatever it is, if I subtract 3, it's obviously still negative. So no negative number can possibly work here. If negative minus 3 is still negative, so it's extraneous. Now the other one, that's the one where, yeah, you would want to plug it into a calculator. And I actually already did the work. I took a calculator and typed natural log of square root of e to the 4th plus 9 minus 3 plus natural log of square root of e to the 4th plus 9 plus 3. I typed it all out. It was a big mess. It does come out to 4. So I did check this one on a calculator. I don't expect you to do it by hand. That would definitely be a calculator question. But our final answer is the positive one only. E to the 4th plus 9. All right, there's one last question I want to go over with you. There's no notes for it. It's a very unique, interesting question, though. I want to show it to you. And I give you a little hint to go with it. It says solve for x, and you have e to the 2x plus 5e to the x minus 6 equals 0. Now, when you look at it, you're like, e to the 2x, e to the x, that looks confusing. So I gave you this hint. I said e to the 2x is like having e to the x squared. And the reason for that, it's the same property we already used once today. When you raise a power to a power, you're multiplying the exponent. So if I took, let's work this backwards. Let's go this way. If I took e to the x and squared it, raise a power to a power, you multiply the exponents, x times 2 is 2x. So when you see this e to the 2x here, you want to think of it as e to the x squared, and then the rest of it is the same. Now the reason that's an important thing to realize is now all of a sudden you look at it and you're like, well, this looks kind of like a quadratic, except instead of having x, it has e to the x. And if I go off to the side here and I say, let's pretend like instead of e to the x, those were both x's. If it was just x squared plus 5x minus 6 equals 0, you guys could solve that by factoring. It would be x, let's see, plus 6 and x minus 1, which would give me x equals negative 6 and positive 1. Well, the only difference between the green and the purple is that it's not actually x, here, here, or any of these. These are e to the x's. But you can solve it the same way. You just have to realize you're not solving for x, you're solving for e to the x. So I could have factored this using e to the x's instead of x's. It still ends up being a plus 6 and a minus 1. But what we've solved for is not x, it's e to the x. Oops, that's a positive 1. So to finish the question, see in green, we would be done. We'd say, okay, x equals negative 6 and 1, and we're done, and we move on. But see, we haven't solved for x. We know what e to the x equals, and you need to separate those and solve them. So you need to say something like, okay, e to the x equals negative 6, or e to the x equals 1. And you could solve both of those by taking the natural log of both sides. And really, I'm going to move these a little so I have some space to do that, with the negative 6 here and the 1 here. So you solve by taking natural log, and you go, okay, well, I can't take natural log of negative 6. I can't do any log of any negative number. So we're going to throw that one away. But on the other side, I get x equals natural log of 1. That's my answer. Although we can evaluate that because natural log of 1 is 0. That's another property, is any log of 1 equals 0. So the final answer to this question is x equals 0. But I wanted to show you that because it's interesting to see that you can factor a quadratic even if it's not an x, if it's something more complicated than x. We factored a quadratic that had e to the x for its variable. Just make sure the common mistake is don't stop here. A lot of people will do the work right, they'll recognize it, they'll go, okay, yeah, I can see, I can kind of factor it, and they'll factor, they'll go, okay, so the answer is negative 6 and 1, they box that up. Just remember, if you're solving by factoring, you are solving for whatever this thing is. And if I ask you to solve for x, see, it says right in the direction, it doesn't say solve for e to the x, it says solve for x. If you solve for e to the x, then you're not finished. You have to keep going until you know what x equals, not e to the x. All right, so today we looked at some more difficult, complicated examples of log and exponential problems solving, and you guys are going to try some of those today.